Hi there, my name is Richard C. Thomas and welcome to my talk, Be More Moog, Tool Design that Empowers its Users. Now, it's quite a hot day, so I've got the fan going. It's just way too hot not to have it on, so apologies for any noise in advance. Let me start by telling you a bit about myself. I'm a 3D artist and I've been working for quite a few years in the industry now. I've worked in various fields, including motion graphics, commercials, and episodic television. I'm passionate about creating CG and also the CG community. In my spare time, I love to work on these creative projects and create tools and write articles about CG. Currently, I'm head of 3D for visual effects for Jellyfish Pictures. We make a diverse set of work. It's been a great year for us. Going to work on some really great projects, including the Book of Boba Fett and Stranger Things 4. We're currently looking for new artists, so check out the website for the positions we have available, and or make a speculative application if you fancy working me and the Jellyfish team. We'd really love to hear from you. Okay, let's get started. The talk was broken into the following sections. Introduction. Here we discuss one of Moog's seminal synthesizers, the Mini Moog, and what I believe made it such an important, successful instrument and tool. We relate it and its development to designing tools in Houdini. We then move on to the main part, a case study of my development of Side Effects Labs PolyWire UV, due to release in 19.5, and see how I use some of these principles in my tool development. The case study is broken into 4 sections. Number 1, structuring the problem, defining modules. We look at the factory PolyWire tool and some difficulties it poses users. We then break down these problems into subsystems, which we can solve for. Number 2, technical iteration. With the starting high-level structure, we discuss a real-world example, how this modular approach helps iterate the PolyWire UV prototype to improve its performance. Number 3, user feedback. Again, with a real-world example, we discuss how the structured and modular approach enabled quick addressing of feedback. Number 4, intuitive and transparent UI design. Looking at the PolyWire UV's interface, we will compare its internal workings, its modular subsystems, and order operations, and how that facilitates actionable feedback from users. With that case study done, finally, we move on to closing thoughts. Like the music instrument designers of the 60s and 70s, as CG tool makers, we have much in common. We are in a changing technical landscape, and through our design, we can empower artists to find new expressions and ways of working to produce new outputs. The Mini Moog and its prototypes mark the transition from the complex, impenetrable machine into a clearly distilled, intuitive instrument, an instrument to make new sounds and new music. Now, the components were not new, but the way they were presented combined and the way they allowed for expression through play and understanding is what made the Mini Moog something new. In some ways, the core framework of Houdini is a bit like conventional modular synthesis prior to the Mini Moog, a huge library of modular parts that could be wired together in mind-boggling combinations. Like the Mini Moog, our job is taking these dazzlingly complex and amazing array of modules to create hardwired combinations of them, and to envisage a control screen to create something new, more than the sum of its parts, that allow artists to do something they could not do before. I think the achievement of the Mini Moog was made possible by 3 key factors. Number 1, the legacy of modular synthesis, which provided a flexible and reconfigurable engineering foundation to quickly allow prototyping. Number 2 is the approach to feedback Moog and his designers had to review the input of musicians. And finally, number 3, design principles of the user interface that reflected the actual flow of data and how sounds were technically formed. We'll touch on all 3 of these factors and relate them back to how they can be applied to create tools that empower artists in Houdini. Here we are in Houdini. Let's start by talking about the factory PolyWire. It's a really great tool. It can mesh curves and can handle branching, scales incredibly well, but there are a few issues that can be an annoyance, especially in certain types of tasks. So let's just start talking about UVs. So by default out of the box, what the PolyWire does is it creates UVs per segment. So if I select tile, you see actually they're all overlapping. Now there are some workarounds to that. You could, for example, take the point number like so and offset. And that looks like, oh, maybe that's going to solve our problem. Now it does for straight lines, but then we start to encounter problems when we get to branching structures. So let's have a quick look at that situation. Here you can see things propagate down nice, and then we get to a problem. And then we're okay, and then things start to go a bit pear-shaped after that. Okay, next, and I've created a point ID attribute and a vertex ID attribute and a primnum. When we look at a geometry spreadsheet, you can see the ID seems to be working okay, but the vertices, no good, no good. And the primitives, again, no good. That makes it very hard to try and fix the polywire downstream. Fundamentally, there's a loss of data that can't really be recovered. Now, another aspect, which is quite challenging, is for the kind of frame, the tangent and the up, and calculating that so we don't get twist. Here we have a very simple scenario whereby it's a circle, everything's left to default, actually it's set to one axis, but you can see we get a little flip and a twist here, around about here. And so this, although, if you do supply good ups, the polywire does a pretty good job, but on branching structures, you can still get these twists. So we have another problem here. Aside from that, out of the box, we don't really get a true sense of length of the curve, how the real world length would relate to the actual U and V. So the U and the V coordinates aren't in scale. So it's very hard to get a uniform distribution of a texture without serious stretching. That leaves us with several clear problems and subsystems which we need to solve for. The first one being how to reduce flipping. The way we do that is creating a frame of reference based on a good up and a good tangent. The second one is resolving and working out the vertex propagation of attributes. If we do that, then we can solve for the primitives as well. Third is solving for the V coordinate, including the accumulation of length and providing options how that is interpreted to form the vertical component of the UV. And fourth is the U coordinate, using that up vector and also the topology to work out a stable U coordinate. So the next step with given those subsystems is try to solve them each one at a time. Generate a first prototype and then try and get some feedback. So let's have a look at that in practice. Here we are back in Houdini. Now let's look how those subsystems played out inside the final tool. Here I've just got to set it up using the lab's branch and tree generators, creating a simple branching structure like so. And here is the current prototype of the polywire UV. And let's just see how the final structure of this relates to those subsystems. So inside the polywire UV, here's the layout. You'll see that there are clear modules of systems that solve specific things to kind of get to us our finished result. First of all, you'll notice there's a few common names like the curve frame and the length and the make U. And so this is how I like to structure tools, with these clear high-level subsystems. So anyone looking inside, it becomes obvious the structure and the data flow. And so if someone's maybe less technically confident or familiar with a problem, they feel like they are orientated and they can feel like there's an understanding of like what is going on. Here it is clearly labeled with the purpose, and you'll see how the tool evolved, and actually those initial subsystems we identified often do actually make it into the final tool. So for example, we have this kind of make U, which is the solve U subsystem, I guess, and very clear layout how that approach is done. So I have this section is the bit that kind of does most of the topology problems to kind of form the U, and here's another section which actually helps to snap the borders at the U together. Now we've got those sections, the subsystems, those modules together. we can now really understand how our tool is performing. Often when you have like a system, it's quite hard to really assess the performance because a particular approach may require a whole different set of components in a certain combination versus another approach. However, we can compare the higher level modules to each other because they have the same function. So this is based on a real world example. This happened when I was developing the PolyWire UV. I was just testing the performance, and so I created a bit of a stress test. Okay, so here we have the pig's head, and what I've got here is a Labs poly slice with an animated number of slices driven by the frame, and then I'm just animating down the width with the frame as well. And what I'm going to do now is go to performance monitor and start recording and seeing how this goes. So as you can see, as the complexity increases, pretty soon this subnetwork here, which I've called old length, it was the original length, it's just the length from a previous version to show you what the problem was, it starts to really increase and eventually takes over the poly wire that creates the mesh internally for the PolyWire UV. And so once we've done that, let's have a look inside. And you see here's the old length I put in to show you. And inside there, and it's very clear that the culprit is the accumulate length. So what that's doing is it's cycling over each connected edge network and then in parallel. And then within that, it's cycling over the primitives from the root to the tip and accumulating length. So this, with complex networks, can really start to be a lot of loops. So I went away, had a bit of think, and then I realized that I could actually change the way that I was accumulating length. I realized that I could actually, like before, cycle over connected edge networks, and then actually store the values of the length inside an array attribute. And so there's no need to kind of dump it back out into the primitives every loop. So once I'd implemented that, this is typically what I do, is I basically just merge these two possibilities together, and we'll see how they get along. Okay, so let's just go through. So we have our old length and our new length. So let's just find those. There and there. So you can see the old length is running at 3.31 and the new one is 0.25. Now, because the components are so different and the approaches, it would be very hard to directly compare, well, it'd be impossible to directly compare these methods in that way if it was a totally flat structure. It's only by really putting things in subnetworks can you quickly and clearly see how things are cooking as a system. And this is something I do quite a lot. I'll typically have a set of inputs that represent a different set of tests, and then I'll run the timeline with the performance monitor on it and see how the tool is performing over a very set of inputs. And again, all only made possible by having these modular subsystems that we can quickly assess one by one and then iterate. Now, what we ended up with after that change is something which I think is pretty decent. Just kind of push it a little bit just to stress test it. And in case you were wondering, there are actually UVs being created. So let's just have a quick look. There they are. So you see them increases as each loop. Okay. So this is another real world example. Whilst I was developing the PolyWire UV, I got some feedback. Essentially this kind of thing was happening. So I've recreated it here. I've got some noisy up vectors and I'm piping them into the PolyWire UV and using the up point attribute setting here to actually make that work. Now, I was of the opinion that really this is to do with what's going in and the artist should resolve and create a good up vector, and then the problem would go away. But it became clear that this is actually quite a difficult thing to do, and to kind of for artists to always understand how to do that is very difficult. So it really felt like we should do something in the tool to resolve that. And so I went away and had a think. For me, this is obviously something which was to do with the curve frame. And I already outlined this module right here. And so I knew exactly where the solution was, and I kind of had a think, and I came up with this idea of a relax roll. Very simply, I basically loop over the curves, and I average the up, and then kind of do a cross product to push it back in a per vertex up, and then cycle that around. And that means that we get this nice little effect here. So you see how it's untwisting itself. And this is a good fallback. So even if someone does apply poor up vectors, they're going to get a good result. Again, this would be quite slow to implement if I hadn't have had that framework in place, if this was just like a flat structure of nodes. And the other thing is, an artist using this and using relaxed rolls and seeing the curve frame and understanding and seeing this is much more intelligible what's going on and where that process is taking place. So here's the UI as it stands. It relates to the actual structure of the poly YUV. So first of all, we have the edge network, and that predominantly is this area here, and that kind of includes the pre-processing of the input geometry and the creation of the up and the curve frame. And then we get to the mesh, which is predominantly just the polywire wrapper, and some other things about what's being exported, and things that relate purely to the mesh. And then we get to the UV section, which happens around here. And finally is the control curve. So the control curve relates specifically to how the incoming curve, which is the edge network, gets restructured and turns into the curve that controls the output. Things that supports the posing and the looking up of the control curve to control the mesh. So the interface is primarily how a user would experience this tool. And by structuring it this way, so it technically reflects what's going on inside, at least during the prototype stage, allows the artist to get an understanding of what's going on. If this interface was maybe based more on purely use of convenience, having buttons that are closer together that are related, then that would obscure the true nature. Now, following that, if that means the way they're understanding what's happening is based on this order, then the feedback tends to relate specifically to the technical workings of how the tool functions. For example, if there's a problem with flipping or rolling, then they're going to talk about the edge network and potentially about the out mode. Although they may not be interacting with this graph directly internally, they're already talking about a specific operation, and the dialogue with the user, the feedback, usually resolves to something which can be achieved without massive overhaul of the tool. Now, by extension, with this interaction of this interface and how it evolves, and the process of prototyping with a developer or a tool maker, their understanding increases. So this is probably the most important thing I want to say, is that by having an interface that relates directly to the structure of how a problem is achieved, it becomes a means for a person to become aware of how one might technically achieve that process. And then in turn, they become empowered with that knowledge to go on and do other things with it. You made it to the end. I'm glad somebody did. We have seen how practically we can apply some simple lessons from Moog and the Mini Moog to empower users and artists, not just with our final tools, but through their design process itself. Now, Houdini has a reputation of having a steep learning curve, but on reflection, I'd much rather have a tool or instrument that assumes less about how I want to work, what I want to know, what I'm capable of, and how I might want to use something. Now, as tool makers, we should be aware as well, from our privileged position, dictating how somebody creates can and often does have a disempowering effect. So it's essential our development process allows for input and feedback at every step to allow us to shift our understanding of the problem at hand. Now, Houdini is one of those rare tools that assumes little about us as users and artists. Houdini, through its design principles, has led me to understand things I thought I never would through the way that I've always learned, experimentation and play. And Houdini also makes it possible for us to engage in a rich conversation of creative discovery between our teams we work with and a wider community of artists and designers. And with care and consideration through our tools and tool making processes, we can shallow that curve. We open new possibilities for ourselves and our users in our tools and development, not just in Houdini, but technically in computer graphics in general. I hope you enjoyed the talk, Be More Moog. You can find me over at Twitter at DoesCG, or you can look at some of my projects at justcthomas.com. Thanks very much, and have a good one.